Good morning, my YouTube viewers. It's Crystal here. I'm just here because I wanted to do a code review with you, and basically what I wanted to go over was nonlinear models. And we're going to look at nonlinear models with regard to TensorFlow and sklearn models. And so that'll be a good thing to do. And so, because, like whenever I work on Kaggle competitions, it's generally a linear model as far as I know. But I wanted to look at nonlinear models because I'm working on a research paper. I'm not actually working on the research paper. I'm reading the research paper. And so in order for me to read the research paper, I have to cover a lot of topics that I don't normally cover on a Kaggle competition. So that's why I'm doing this. So the first nonlinear model that we're going to look at is going to be with TensorFlow. So you're going to import NumPy as NP, import TensorFlow as TF, and import matplotlib.pyplot as PLT. And then what we're going to do is we're going to generate the synthetic data with a nonlinear relationship. So we've got the code here, np.random.seed is 42, nsamples equals 100, x equals np.linspace, neg5, 5, nsamples, y equals np.sin x plus 0.5 times x plus np random.normal 0.2 nsamples. So that's the nonlinear relationship of the data. And now what we're going to do is we're going to standardize the data. And so x norm equals x minus np dot mean dot x over np dot stdx. Y norm is y minus np dot mean y over np std y. So we've standardized the data. And now what we're going to do is we're going to define our neural network. It is a sequential neural network. On the hidden layer, it has activation as ReLU, and then the output layer is it says it's linear, but it's not linear, and it's 1. And then after we have created our TensorFlow model, which is a sequential model, we're going to compile the model with mean squared error and atom loss optimizer. And then after we've compiled the model, we're going to train it for 200 epochs with a batch size of 16 and verbose equals 0. So we're going to predict on the model. So y pred norm equals model dot predict x norm, and then y pred equals y pred norm times np std y plus np std mean. And then we're going to check the RMSE. So let's just say So we're going to obtain the root mean squared error. And that was 1.4867775. And then we're going to plot the data and the truth line and the neural network approximation using matplotlib. So you can see that. You can see the data, and you can see the truth line, which is the green line. And then you can see the neural network approximation. And so you can see that the neural network approximation is kind of edgy, really. But that's what we got with TensorFlow. Now what we're going to do is we're going to talk about decision trees. And decision trees is using the same the same data that we used for the TensorFlow model. It's just that instead of a TensorFlow model, we're going to use a decision tree regressor. And then we had to make XNorm a data frame for that to work out. And we checked the RMSE, which is 1.4957 blah blah blah. And this is what it looks like with the decision tree. So what that's saying is it's overfitted is what's happened, because like whenever it fits each and every piece of data, it's overfitted. So what you could do here, let's just see what we've got here. Come over here to the decision tree regressor. It says max depth none, maximum depth of the tree. Then it expands until all leaves are pure or until all leaves contain less than the min sample split. The min sample split is 2. The minimum number of samples required. So I'm going to say a max depth is 2 here and see what happens. It might not improve, but let's just see what happens. Let's see if it works. It says XNorm is not defined. Try to run it all. It's doing something. So there we go. When we made max depth equals 2, it didn't overfit it, but it still doesn't look fantastic. So that's your decision tree. Let's try max depth equals 1. Nope. Let's try max depth equals 3. So there's your max depth equals 3. Let's try max depth equals 4. So there we go. That's max depth equals 4. That looks a bit better than the initial one, because the initial one was overfit. So now what we're going to do is random forest regressor. And this is what it looks like with random forest regressor. So you can see that that is overfit as well. We can come over here. Come over here to random forest regressor. Max depth, we'll make max depth equals 4 again. Let's try it again. So that looks a little bit better than, it's not quite so overfit. And so you can adjust the fitting by setting the max depth. But let's try max depth equals 5. So that looks a little bit better too. So we'll come over here to the decision trees. And we'll try max depth equals 5 here on the decision tree. So you can see that looks a little bit better too. But you can see that the more that you fit the max depth, the more fitting it goes through. So in a max depth 1 or 2, it might be underfit, but a max depth 5, is veering towards being overfit. Now let's check the support vector machine. And look at that. The support vector machine is very close to the true nonlinear relationship. So that looks like a good fit there. But we'll keep looking. Let's check k nearest neighbors. K nearest neighbor equals 5. You can see that I put it k nearest neighbor equals 5, and you can see that that looks pretty close as well. Now this is MLPR, that's multi-layer perceptron regressor, and this is sklearn's regressor, sklearn's neural network. So we set it up for hidden layers of 150, max iterations of 1,000, solver equals LBFGS, random state equals 42, and there you go. There's the MLPR. And I think that the MLPR worked better than TensorFlow. And the reason why is because we saw the solver was LBFGS, and I didn't see an LBFGS for TensorFlow. So since I didn't see an LBFGS for TensorFlow, I couldn't use it. So that looks like a very good fitting. Now we're going to do the Gaussian process regressor. So the Gaussian process regressor looks like a very good fit as well. We're going to do the gradient boosting regressor. So you can see the gradient boosting regressor is very close to being overfit. Let's look over here for says max depth default equals 3. So let's set the max depth default equals 5. See what happens. Wow. Look at that. So that's overfit, looks like. Try it, max depth equals 4. So you can see it's still fitting, still on the verge of being overfit. And then max depth default equals 3. So there you go. That's your gradient boosting. Now we're going to check polynomial regression. And you have to use polynomial regression with linear regression. And I had to study this a lot to get it to work. But this is how to do polynomial regression with a nonlinear model. And so we set it up for degree equals 5. And you can see with the degree equals 5, it's very simpler, and you had to use linear regression with that. So poly equals polynomial features, degree equals 5, include bias equals true, x norm trans equals poly dot fit transform x norm, L reg equals linear regression, fit x norm trans y norm, and then you predict on it. Y pred norm equals L reg dot predict x norm trans, and then we take out the standardization. Y pred equals Y pred norm times np dot stdy plus np dot stdy, and then that takes out the standardization. And then look at that. That looks very close to the original line. And so that's it. Polynomial regression is the last one that we used. And you have to use polynomial features with linear regression to do that. So that's it. That's it for this code review. I'm going to go ahead and conclude the code review because we've covered all of the different models that I could find that work on nonlinear regression, and you can see for yourself which model works the best. I think that polynomial regression worked really good and SVM worked really good, and all the other ones had varying degrees of success. And I think that every time you work with a nonlinear model, you need to select nonlinear data, you need to select several different models and to test on, and then choose the one that gives you the best reading. Whereas we got SVM and polynomial regression gave us the best outcome that I could see. So thank you so much for watching my video. If you like my video, please like, subscribe, and share. Thank you to my subscribers for supporting my channel, and I look forward to making more code reviews for you in the future.